Hello guys, welcome back to Organic Chemistry Exams Prep. So we are currently discussing the reactions of organometallic reagents. So basically there are three main types of organometallic reagents that are important for undergraduate chemistry classes or competitive exams. One of those is the Gilman's reagent, which we have already discussed, and the second type is alkyl lithium type of reagents, and the third type is Grignard reagents. So we are going to discuss now the Grignard reagents. So the method of preparation of Grignard reagents is simple. You have your starting compound alkyl halide as your starting material, or X, where X is either chloro or bromo or iodo group, and R group or the carbon group may be alkyl, it may also be alkenyl like vinyl, and it can also be aryl, for example phenyl group. So the starting compound alkyl halide reacts with magnesium metal in presence of dry ether or tetrahydrofuran. So these are common solvents used for preparation of Grignard's reagents. The Grignard's reagents general formula is RMgX, and since the magnesium, it's a metal, so it's more electropositive, therefore the carbon part, it gets a partial negative charge. So overall the Grignard reagents, just like the Gilman reagents, act as nucleophiles, and so the Grignard reagents will also react with electrophilic carbon centers. So there are four main types of reactions of Grignard reagents. The first of which is nucleophilic addition on a carbonyl carbon. So this is one of the most important reactions in which we have either an aldehyde or a ketone, and we react that in two steps. First step is the reaction of aldehyde or ketone with the Grignard reagent, and second step is the acidic workup. So this reaction gives us from aldehyde or ketones, it converts to secondary or tertiary alcohol. So the mechanism of this reaction is there are two steps. First step is the nucleophilic addition of Grignard reagent to the carbonyl carbon, and the second step is the acidic workup. So here, as we saw earlier, carbon is the nucleophile, so it approaches from the opposite side of the carbonyl oxygen bond, and in this step, once the nucleophile attacks the electrophilic carbon, this pi bond breaks and you get the tetrahedral intermediate. Now this tetrahedral intermediate quickly will grab a proton from the acid present in the second step, and that would give us a tertiary alcohol. So in this reaction we haven't shown the general structures, but a specific structure of a ketone which gives us a tertiary alcohol. Now the second type of reactions where we have addition of the nucleophilic Grignard reagent is the addition of Grignard to the carbon dioxide. So there are two steps here. First step is the nucleophilic carbon approaches the carbonyl group of the carbon dioxide, just like we have seen above in the mechanism, and In second step, again the acidic workup gives us the carboxylic acid product. So these are two reactions, but broadly we can classify them as one reaction, a nucleophilic addition on a carbonyl carbon. So Grignard reagents general formula is RMgX, where this bond between this carbon and metal, it's very polar. It's got a very good ionic character. So because the magnesium is more electropositive, so it gets the partial positive charge, and the carbon gets a partial negative charge. Because the electronegativity of carbon is higher than the magnesium, therefore this shared pair of electrons is more towards the carbon. So now as we see that, just like the Gilman reagents or alkyl lithium reagents, the Grignard reagents are also nucleophilic in nature. So the nucleophilic compounds or species would react with the electrophilic compounds or species. So we have seen the first reaction, which is nucleophilic addition on carbonyl carbons. So this is one of the most important reactions of the Grignard reagents. So our aldehydes, when reacting with Grignard reagents, would give us secondary alcohol, and the ketones would always give us tertiary alcohols. The primary alcohol is obtained only when a Grignard reagent is reacted with formaldehyde. Other than that, all aldehydes would convert to the secondary alcohols, and all ketones would convert to the tertiary alcohols when reacting with the Grignard reagents. So now the second type of reaction, this is also important, the nucleophilic substitution and subsequent addition on the esters and acyl halides. So this is a double addition of the Grignard reagent, and the product of this reaction is tertiary alcohols. So here we have seen the structure of an ester, but if this ethoxy group is Cl, then this would become an acid halide, acid chloride to be precise. And again, just like before, there are two steps to this reaction as well. First step is the addition of here it's methyl magnesium bromide, and second step is the acidic workup. So if there were to be just addition of one Grignard reagent, then that would be the case. However, here there are 4 steps to get the product. So now let's see one by one the 4 steps. So our first step is the nucleophilic Grignard reagent attacks the electrophilic carbonyl group to form the tetrahedral intermediate. Now this first step is the addition of Grignard reagent. The second step is the substitution step, where the tetrahedral intermediate collapses and the leaving group leaves as ethoxide ion. So this step is the elimination. Now this elimination gives us the product, which is a ketone. And ketones are even more reactive than esters, which we will see in a minute. But let's finish the third step here. Third step is again the addition of Grignard reagent. So once again we get the tetrahedral intermediate, and this time because of acidic workup step, this alkoxide ion gets a proton to become tertiary alcohol product. So this is our fourth step, which is simply the acid base reaction. So this base takes a proton to become neutral. So now to recap this mechanism, it has 4 steps. First step is the addition of the Grignard reagent to the electrophilic carbon. The second step is the elimination of leaving group. Third step is the addition of Grignard reagent, and fourth step is the acid base reaction to neutralize the alkoxide ion formed as an intermediate in this reaction. So now this addition of Grignard reagent takes place twice. The reason for that is that the ketones, they are even more reactive than the esters. So towards the nucleophilic addition reactions, of course. So we can see the resonance structures here. So if you have a ketone, so we can show the resonance like that, because oxygen is more electronegative than the carbon. So this pi bond is more towards the oxygen. Therefore, the result of this resonance movement, or the movement of electrons, gives us this resonance structure, which is quite stable, and we can show how the resonance hybrid would look. So this carbon gets a partial positive charge and oxygen gets a partial negative charge. Now, in case of esters, the first resonance is similar. So the oxygen gets a negative charge and the carbon gets a positive charge. So this is similar to what we saw in case of a ketone. But there is another possibility here, further resonance, that is due to this oxygen here. So the lone pairs on the oxygen would make a pi bond here between the carbon and oxygen, and hence this oxygen gets a positive charge. And although this is not very stable, and this is a minor resonance structure because the oxygen is very electronegative and it doesn't like to have a positive charge. Oxygen, on the other hand, likes to have a negative charge. So now for the resonance hybrid, we can show that this oxygen gets a partial negative charge, the carbon gets a partial positive charge, and this partial double bond, this oxygen also gets a partial positive charge. So now we can see that there is only one resonance structure here, other than the, of course, starting structure. But in case of esters, there are more than one structures. So that's the reason that if you see this resonance hybrid, it clearly shows that the positive charge is not concentrated on the carbon only, just like it is in the case of ketones. So the positive charge is spread out throughout the molecule, especially a part of it is also on the oxygen of the ethoxy group in the ester. So that's the reason that it's not very electrophilic. So it's less electrophilic than the ketone. And that's the reason that ketones are even more reactive than the esters towards nucleophilic additions. Currently, we are discussing the organometallic reagents. organometallic reagents have a carbon metal bond. The metal here could be lithium in case of organolithium compounds. It could be a copper in case of Gilman reagents, and in case of Grignard reagent, it is magnesium. So this carbon metal bond being very polar, it's got some ionic character to it. So the metal being electropositive could be considered as partial positive and the carbon is partial negative. So that's the reason that our organometallic compounds are nucleophilic in nature. So the nucleophiles will react with electrophilic centers or species. In this case, they would react with electrophilic carbon of aldehydes and ketones, esters, acyl halides, and epoxides. So the first type of reaction that we saw were the reactions of Grignard reagents with aldehydes and ketones. So Grignard reagents would add on aldehydes and ketones to form primary, secondary, or tertiary alcohols. In case of formaldehyde, they form primary alcohol. In case of other aldehydes, they would form secondary alcohols. And in case of ketones, they would always form tertiary alcohols. The second type of reactions were the reactions of Grignard reagents with esters and acid halides. The Grignard reagents would add twice on these compounds. The reason is that the intermediate compound that forms is a ketone, and ketones are even more reactive than corresponding esters or acid halides, and that is the reason that Grignard reagent would add twice on them to form tertiary alcohol. Now, the third class of reactions of Grignard reagents are reactions with epoxides. They are also known as epoxide ring opening reactions to form alcohols. So this reaction is very important because here we are forming a new carbon-carbon bond on an sp3 carbon, which means that we are increasing the length of the carbon chain. And these reactions are important because in organic synthesis, our goal is to make bigger, more complex molecules containing the functional group so that they could further be applied to different scenarios, to different applications. And one of those applications are applications of organic compounds in pharmaceutical reagents. They could also be used in some organic photovoltaic solar cells, or their applications could be just simply understanding the fundamental science of organic synthesis. Now, in this reaction, here we have an example of a symmetrical epoxide. So if you have a symmetrical epoxide, it's got two carbons, so both carbons are equivalent. So in this reaction, the Grignard reagent can approach either carbon and you would form the same product, primary alcohol. In case of an asymmetrical epoxide, you are having here two choices. So this one is our primary carbon and this is our secondary carbon. So the primary carbon is considered a carbon that is connected to one carbon or no carbon, and secondary carbon is a carbon that is connected with two carbons. Here we have this primary carbon which is less hindered, and this carbon here is more hindered. So less hindered versus more hindered. Now, our Grignard reagent is nucleophilic, and the carbon that is connected to epoxide is electrophilic. So we have two options, and now as you see the product, our product is a secondary alcohol, which means that our nucleophilic Grignard reagent has been connected to this primary carbon. And the reason for that is, if you see the mechanistic steps, this is simply a substitution nucleophilic second order reaction. And we know that SN2 reactions, in SN2 mechanism, the nucleophile approaches the sterically less hindered carbon. And so this SN2 reaction, this step, it's got two steps. First step is the substitution step. The second is the neutralization step. So the first step is the nucleophilic substitution. The second step is the neutralization. So first step is the slow step. And the second step, acid-base reaction, is the fast step. So the slow step of the reaction mechanism is the rate determining step, and the first step is not rate determining step. So in this mechanism, the nucleophile attacks the carbon which is less sterically hindered. Once the nucleophile attacks, the leaving group leaves. So this epoxide opens and you form the tetrahedral intermediate, which is an alkoxide ion. So this alkoxide ion has an oxygen with a negative charge, which is a very good base. So in the neutralization step, the base takes a proton from the hydronium ion that is present due to the acid workup to form the product, which is a secondary alcohol. So the general formula of the Grignard reagent is RMgX, where R could be an alkyl group or aryl group or a vinyl group. X is a halide, which usually is either bromide or chloride. The iodides are less common. So the bond between the metal and carbon in this organometallic compound is very polar. So it's got some ionic character to it, and therefore the carbon, being more electronegative, gets a partial negative charge here, and the magnesium, being a more electropositive than carbon, would get a partial positive charge. So now it's easy to understand why the Grignard reagents would be good nucleophiles. Now the question is, why are they strong bases as well? So to answer that question, we need to see the structure of our Grignard reagent again. So if we break this bond heterolytically, the bond pairs of electrons would go with the carbon, and you would form a carbon ion plus magnesium halide cation. So the example would be a methyl magnesium bromide. So in this way, it's easy to see why this would be a very strong base, because this is conjugate base of a very weak acid, and we know that weak acids would give very strong conjugate base and strong acids would give a very weak conjugate base. Now, so far we have seen the reactions of Grignard reagents with carbonyl carbons. We have seen the reactions of Grignard reagents with aldehydes, ketones, carbon dioxide, esters, acid halides, and epoxide. So the aldehydes and ketones would react with Grignard reagents, and it's a two-step reaction. First step is the addition of nucleophilic Grignard on aldehydes or ketones carbonyl group, and the second step is the acidic workup. So the aldehydes would give you a primary alcohol in case it is a formaldehyde as a starting compound, and other aldehydes would give you a secondary alcohol. All ketones would always give tertiary alcohol as the final product. The carbon dioxide, however, is different in a sense that it does not give alcohol as final product, but the product of Grignard with the carbon dioxide is a carboxylic acid. Now for the esters and acid halides, because they got a very good leaving group in them, therefore the Grignard reagents would add twice to give tertiary alcohols. And finally, epoxide ring opening. These reactions are SN2 type of reactions, where the Grignard's methyl here, for example, is a nucleophile which opens the epoxide ring. So depending on the type of epoxide, you may have primary or secondary or tertiary alcohol. Now let's have a look on fourth type of reactions of Grignard reagents, and those are acid-base reactions. So Grignard reagents, being a very strong base, would react with proton donors, for example, water, alcohol, acids, amines, and alkynes. In these reactions, the hydrocarbons of the corresponding Grignard reagent forms, and so this is a type of synthesis of hydrocarbons by using Grignard reagents. So to understand these reactions that we have here, several acid-base reactions of Grignard reagents, we need to quickly review the Bronsted and Lowry acid-base concepts. So Bronsted-Lowry acids are the species that can give protons. So the examples would be hydrochloric acid, sulfuric acid, alcohol, carboxylic acid, and so on. Now, the Bronsted-Lowry bases are the species that can accept protons. So the examples would be ammonia, amines, chloride ion, hydroxide ion, and similar species. So now let's see one example of how these Bronsted-Lowry acids and bases react. These reactions are known as neutralization reactions. So one of the examples that we can take here is the reaction of ammonia with the hydrochloric acid. So ammonia is a base. It reacts with hydrochloric acid to give ammonium ion and chloride ion. So the base is ammonia, so once it gets the proton, it makes the conjugate acid ammonium. This is called the conjugate acid of our base. Now the acid was hydrochloric acid, so its conjugate base would be the chloride ion. So this would be the conjugate base of hydrochloric acid. Alright, so let's have a look on some of the reactions of Grignard reagents with the proton donors. So the first reaction is we have ethyl magnesium chloride as our Grignard reagent. It reacts with water. Water's pKa is about 14, which means that it is not very acidic, but it can give a proton to become a Bronsted conjugate base. So the basic Grignard reagents carbanion part takes the proton, the bond between oxygen and hydrogen breaks, and the corresponding hydrocarbon is formed. The byproduct of this reaction is the magnesium salt of chloride and hydroxide ion. Now the second reaction is the reaction of Grignard reagent with heavy water. Heavy water has deuterium isotope instead of the hydrogen in it. So it's D2O instead of H2O. So the similar reaction would occur. The base would take the deuterium and a hydrocarbon is formed where you have introduced a deuterium in it. So it's quite interesting to see the introduction of deuterium to a hydrocarbon. Now the third type of reaction is the reaction of Grignard base with the alcohol acid. Alcohols are a bit less acidic than water, so their pKa is about 16. So here we have ethanol, so this bond would break and you would form the hydrocarbon. See the color code here. So the proton is denoted in red, and the other part, remaining part of the compound that gives the proton is noted by blue colored atoms and bonds. Now the fourth reaction here we see is the reaction of Grignard reagent base with a carboxylic acid. So here we have shown the acetic acid whose pKa is 4.7. So again, base takes proton to form the corresponding hydrocarbon. In this case, it is benzene. Now, next reaction is the reaction of Grignard reagents with the primary and secondary amines. So a primary amine is an amine where nitrogen is connected to one carbon or one carbon chain. This is primary amine. Secondary amine is an amine where there is a nitrogen connected with at least two carbons or two carbon chains. Now the pKa of these amines is about 35. So again the base takes the proton from the amine and hydrogen bond breaks to get the corresponding hydrocarbon. In this case, the Grignard reagent was isopropyl bromide, so you get the isopropane here. Now the tertiary amines are the amines where there is no hydrogen on them. So these are called tertiary amines, where the nitrogen is connected with 3 carbons or 3 carbon chains. So tertiary amines, since they don't have hydrogen on them, so they are not proton donors, so they would not react in this manner with the Grignard reagent. Alright, so the next reaction that we have here is the reaction of Grignard reagent with an alkyne. So the alkyne has sp carbon in them, and the hydrogen is connected to the sp carbon, and sp carbon is more electronegative than sp2 carbon and sp3 carbons, and that's the reason that its conjugate base is more stable. Hence the hydrogen is more acidic than alkane's hydrogen and alkene's hydrogen. So in this reaction, the Grignard reagent would attack the proton, and the product is again a hydrocarbon. But here there is an interesting point to note that we are forming another Grignard reagent, and this Grignard reagent has a triple bond in it in carbon part. So this has a very good synthetic utility.